In this lesson we're going to look at the law of refraction. This is also known as Snell's law. Now we remember that refraction takes place when a wave, and by wave we can mean, for example, a light wave or a sound wave, a seismic wave or a water wave, changes direction as it crosses a boundary between two different mediums. Okay, they have to be different mediums. So for example here we've got a glass block. So our medium here is glass, and then we have another medium here which is air, and again air the other side of the glass block. Now in this particular case we're looking at light waves, and we're going to represent the light wave using a ray like this, and we can see that the ray is about to change medium from the air into the glass block. Now this changing of direction or refraction will only take place if the ray is incident on the boundary at an oblique angle. It won't take place, for example, if the ray hits the glass block head on like that. So it has to be at an oblique angle. Now in order to show the law of refraction we need to define some angles here. So first thing we say that the ray is incident on the glass block, and we're going to define a line called the normal. We'll write normal, and the normal is a construction line that is exactly perpendicular to the surface at which the light ray is incident. So we'll write that there, that's perpendicular to that surface. And we're going to call the angle between the normal and the light ray there the angle of incidence, and we'll represent that with the letter I. Now I should point out that we'll extend the normal through the boundary like that, and as the ray passes across this boundary it then changes direction, that is refraction. Now if you want to understand better how or why that happens, then I suggest that you look at the previous lesson, which gives an explanation to this bending of the ray. In fact, if you haven't watched that video, then I suggest that you stop this one straight away and watch that one first. So the light ray is then refracted, and you'll notice that when it's refracted it changes direction, and so we call the angle between the normal and the refracted ray R, or the angle of refraction. Now you'll notice that whenever the light ray passes from a less dense medium such as air to a higher density medium such as glass, then the angle of refraction is always less than the angle of incidence. Now you'll observe that we have a glass block with parallel plates, so when the light ray passes back again from the glass medium back into the air medium, it will be travelling in the same direction as the initial ray, and we can construct the normal again to that surface. So this now becomes the angle of incidence, and this becomes the angle of refraction. And you'll notice now that as the ray travels from the high density to the low density medium, then the angle of refraction is now greater than the angle of incidence. Now in this lesson we're talking about the law of refraction, so we want to find a relationship between the angle of incidence and the angle of refraction as a ray passes from one medium into another. Now to do that we have to introduce another term called the refractive index. Now the refractive index of a material is denoted by the letter N. Okay. So the glass has a refractive index and the air has a refractive index. In fact, the refractive index of air can be considered to be equal to 1. It's not quite 1, but from our point of view we'll consider it as 1, and the refractive index of most glasses range from about 1.4 to typically about 1.7 or 1.8, but typically round about 1.5. But anyway, we assume that this glass has got a refractive index and it's represented by the letter N. And the refractive index really is a measure of how much the light interacts with the material as it passes through it. Now, a material which has got a high refractive index means that there's more interaction with the light, and as a result the light tends to slow down more as it passes through the material. And a material with a lower refractive index interacts less with the light, and as a result the light beam slows down less. Now, this slowing down of the light is exactly what results in this change in direction. So the more the light is slowed down, the more it is bent as it passes from one medium into the other. That might again sound a little bit hard to digest at this stage, and again I suggest that if you want to get a better understanding of this, then you look at the previous lesson, which explains how this changing in direction results from a slowing down of the light as it passes between the mediums. What is important now anyway is that the material has got this refractive index, and there is a relationship between the angle of incidence and the angle of refraction and the refractive index of the material, and it is this. So let's take it step by step. As the ray passes from the lower density medium of air into the higher density medium of glass. So we will say that first of all we take the refractive index of air, and we'll just write a little air down there. That tells us it's the refractive index of air multiplied by the sine of the angle of incidence. Is equal to the next medium, which is the refractive index of glass, which we'll just call n, multiplied by the sine of the angle of refraction. And there we have the law of refraction. Now you'll notice that, as I said earlier, the refractive index of air is equal to 1. So we can forget this term, and we can write this as sine of I is equal to n times the sine of r. Now, in many GCSE type questions, and I've reviewed quite a few, it seems to me that one of the things that they typically ask you is to find the refractive index of a material, knowing the angle of incidence and knowing the angle of refraction. So we might like to write this expression as this, saying that the refractive index of the medium is equal to the sine of the angle of incidence divided by the sine of the angle of refraction. Let's have a look and see what happens when we come out the other end. Okay, so this time we've got the angle of incidence is actually inside the glass. So this time we write the expression as the refractive index of the glass, in this case is n, multiplied by the sine of the angle of incidence, is equal to the refractive index of air multiplied by the sine of the angle of refraction. Now we've written it this way round because now the refracted ray is in air and the incident ray is in the glass. Then again, as before, we remember that the refractive index of air is 1, so we can rewrite this expression as n times the sine of the angle of incidence is equal to 1 multiplied by the sine of the angle of refraction, or simply as sine r. Okay, remember that this is equal to 1. So in this case, let's say going from the high density medium into the low density medium, we now write n as equal to the sine of the angle of refraction divided by the sine of the angle of incidence. That's because we're going from the high to the low medium, whereas before, in this expression, we were going from the low to the high medium. So you've always got to think about whether the ray is going into the glass or whether the ray is coming out of the glass, as in this case.